So, this is my beam with fixed at both the ends, xm and ym. There is an ith member, the length of the member is Li. I give unit rotation at P alone, keeping all other degrees of freedom restrained. So, I give unit rotation, I draw a tangent, I measure this as theta p, which is unity. Now, this will invoke members with end forces. I call this as K P P of the ith member. I call this as K Q P of the ith member. This value will be K R P of the ith member, and this value will be K S P of the ith member. Let us try to understand how did we get this notation. Take for example, this notation K I P P. What does it mean? This is actually force in pth degree of freedom. Okay. So, the first P represents this by giving unit displacement in pth degree of freedom. The second one represents this, and this notation represents, this is meant for the ith member. Similarly, one can read this force in qth degree of freedom by giving unit displacement in the pth degree, and similarly this will be force in the rth degree of freedom by giving unit displacement in the pth degree, and this will be force in the sth degree of freedom by giving unit displacement in the pth degree. How did we get this PQRS? Please look at this convention. PQRS are what we have already taken. The rotation is called as P and Q, and the displacements translational are called as R and S. So, I am using the same thing here. This is P and P, Q and P, R and P, S and P. So, there is one more important thing I want you to observe. You can see the second subscript in all the notations in K P P, K Q P, K R P, K S P. The second subscript in all the notations is P, is common. The second subscript is common, which is P here, which indicates that we have given unit displacement at pth degree. Okay. So, on the other hand, you will see that the stiffness coefficients will be generated column wise. Okay. This is the first column now, because all the second notations of this are same. It is similar to A11, A21, A31, A41, which indicates it is the first column and different rows. So, stiffness matrix will be generated and the coefficients are prepared and derived column wise. Okay, that is very important. Now, let us find out these values. I have given unit rotation at the end j, and I have got KPP, KQP, KRP and KSP. Okay. Similarly, I can also draw for unit rotation at theta q. So, I will try to get the moment directions as K QQI, K PQI, K RQI and K SQI. You can note down the second subscript in all coefficients or Q, which implies that we have given unit rotation at qth degree of freedom. So, this will be imposing unit rotation at end k of the member. Okay. So, that is this figure. Similarly, I can also cause unit displacement at the jth end and unit displacement at the kth end. So, let us say I want to create a unit displacement at this end So, this is going to be unity. So, this will impose moment which will be K P R I, which will be K Q R I, and this will be K R R I, and this will be K S R I. Similarly, on the other hand, let us try to have unit displacement here. Say this is my delta S, which is unity. So, now I am going to mark the degrees of freedom and the moments, which is K Q S I, which is K P S I, which is K R S I, and K S S I. Interestingly, I can also draw a tangent between the initial and the final line of the beam, and I can say that the beam has undergone indicates a rotation which is actually 1 by Li, where Li is the length of the member, which is also now equal to 1 by Li. Okay. We will also have the same fashion here, which is 1 by Li. Similarly, we can also do this by joining the initial and final line of this member and saying that this rotation is 1 by Li, which will cause rotation here and here, which will be again 1 by Li and 1 by Li. Okay. So, for completion's sake, let us draw this figure also back here. So, this is unit rotation or unit displacement at jth end. This is unit displacement at kth end, and let us draw this figure for completion's sake in the same sketch and give unit rotation here. So, this is going to be K P P I, this is going to be K Q P I, this is going to be K R P I, and this is K S P I, which is same as this figure which I have just reproduced here, and I am saying the title as unit rotation at jth end of the member. Okay. So, there are 4 figures. This is actually figure 1, this is figure 2, this is figure 3 and this is figure 4. I am sorry for the order, but this is what already we explained the last slide. Okay. Now, we have 4 figures. Our objective is to find out these stiffness coefficients for unit displacement and each degrees of freedom. Okay. Let us write down the compatibility equation for ith beam element experiencing arbitrary end displacements, namely theta p, theta q, delta r and delta s, as shown in the figures. Corresponding end reactions. What could be the end reactions? It could be the moment, it could be the shear. Okay. Or required to be estimated. That is our job. Okay. They need to be estimated by maintaining equilibrium of the restrained member. So, we need the governing equation. They are as follows: MP, that is the end moment of the ith member in the pth degree of freedom, will be Kpp theta p plus Kpq theta q plus Kpr delta r plus Kps delta s. So, one can very easily see here, if you talk about the end moment at pth degree of freedom, all will be related to p and contributions from each degree like p, q, r, s have been taken. The moment you say the second subscript is p, you get theta p, q theta q, r delta r, s delta s. We also know p and q are rotations and r and s are displacements. So, I am using theta for rotations and delta for displacements. In the same order, now we can write MIQ. I expect you to write this, it is very simple. So, since it is q, all first subscript will remain as q. So, KQ. So, if say p theta p ith member plus KQQ, therefore, theta q plus KQR and therefore, delta r of the ith member plus KQS delta s. Very good. So, that is what we have to write. It is very simple to remember if you understand the notation very carefully. Okay. Similarly, I want to find the force, that the shear at r at the end. So, obviously, this is going to be the first subscript is going to be r, caused because of p, second subscript is p and theta p. So, r q theta q plus r r delta r plus r s delta s. Okay. I do not think any confusion in this. Similarly, the fourth one P s I. So, K S p theta p, K S q theta q plus K S r delta r plus K S s delta s. I think that is what it is done. So, I call this equation as equation of set 1. So, what are these equations giving me? These equations are giving me the end moments and end shear for arbitrary displacements theta p, theta q, delta r and delta s, which are unity at respective degrees of freedom, and we are trying to find out the forces. The moment I say these displacements are unity in magnitude, these reactions will actually become nothing but the stiffness coefficients which are evaluated, and they will all be the forces or the end reactions, and each one of these value will be the stiffness coefficient. So, now I can generalize this equation by a statement saying m I will be k I into delta I, the generalized equation, okay, where m I vector is actually m p, m q, p r and p s, and delta vector is actually equal to theta p, theta q, delta r, delta s, and k I will be the stiffness matrix, which will be k p p, k p q, k p r, k p s, k q p, k q q, k q r, q s, k r p, r q, r r, r s, s p, s q, s r, s s. To remember this, let us use some shortcut method to really reproduce this in a simple term. Please remember this, it is very easy. I call this as P, Q, R, S columns, okay, these are all columns, and I call these rows also as P, Q, R, S, okay, these are rows. Okay, it is a 4 by 4 matrix. So, if you want to remember this, it is very easy, row first, column next. So, Q R, row Q, column R. So, I can easily reproduce this matrix. So, I can rewrite this matrix in a very simple form, simply understanding saying P, Q, R S, P, Q, R S. If you want to really write down this element, this element will be actually K, row first and column next, which is similar to exactly this. So, now this equation what we derived is a fundamental expression for a beam element. Our job is to now find out what would be these stiffness coefficients by giving unit displacement and the respective degrees of freedom. So, friends, let us look at the summary of this lecture. In this lecture, we introduced the conventional beam element, which is actually a fixed beam. We also recommended certain sign conventions which are required to follow the derivation. We expressed in simple terms how to derive k I j graphically, and then we landed up in an expression saying m I is k I of delta I, where I represents the whole event for the ith beam. So, there can be n number of such elements in a given frame. I hope you have understood this. I want you to browse through this very quickly and understand once again how we have followed this, and I hope we will continue to discuss more in detail in the next lecture. Thank you.